Okay. Okay. Okay, you guys. Attention. I can't scream. All right. Some days you're more talkative than other days. Is there any reason why? Sometimes you're quiet and sometimes you're energetic. Can maybe. Ah. Okay, so I have an announcement. There will be a midterm next week. No, no, I'm kidding. So one of you emailed me about potentially postponing the due date for the moisture lab just because of the back and forth with the Excel file and the data. So I thought it's okay. You can submit by Monday, not next Friday, not this Friday, Monday. But it will be open on Friday if you want to get it done and submit it. You're welcome to. If you need the extra time, you have it till Monday. Okay, good. Sarah is going to finish up ASH content or ASH analysis, and I'll start right after she's done with facts. So, yeah, all yours.
Hello everyone again, and then for the last time we mostly discussed about the dry etching using the muffle oven, and then this time we will continue with the wet etching. Did you remember why we were conducting the wet etching? What was the purpose to do the wet etching? Did you remember that I mentioned last time a few times? Yes, Sash. Yeah, one of the reasons was during the dry etching, we may lose some sample through the volatilizations, thus we cannot do the exactly what we are looking, but the exact answer do we have? Yeah.
For mineral content analysis?
Yeah. Specifically, if we are looking for the mineral profile of the, if we are specifically looking for the mineral profile, the sample that we are analyzing, we're supposed to do the wet etching. So the overall, the wet etching was a procedure. If you want to check the mineral profile of the sample, that you need to use this methodology. Basically, what are the components that we are doing for the wet etching? Basically, it is also called as like wet oxidation or digestion. We use some combination of the acids. These are basically, we can see like combination of the caloric or sulfuric and nitric acids to digest the sample, to remove the organic components, and then to get the inorganic substances to overall to check the minerals. And then when we are conducting this experiment, we're supposed to always have the reagent blank, but for the dry etching, we don't need to do the blank. Overall, these three things that we need to remember. And basically, our assay will be a combination of one of the acids like nitric, perchloric, or sulfuric nitrate. And then for these experiments, we don't need to use the oven like for the dry etching that needs to reach like 550 Celsius. For this one, we are just digesting the sample about 2 hours at 200 Celsius using the hot plate, of course, under the hood. Then the couple of reactions, when it is done, at the end, we are going to get the like strawberry yellow solution. That solution will have the minerals that we are looking for. This is the overall how we are getting the assay. And then for the lab, maybe you are going to do the wet etching, then you can see the entire procedure depending on which official method that you are using. And there are the several advantages and disadvantages for the wet etching. Overall, as we mentioned before, there is not volatilization which is happened during the dry etching. Thus, we can definitely get the better mineral profile that we are looking for the sample. And also the minerals, yeah, at the end, it stay in the yellow colored solution. And then oxidation time is about 2 hours, basically, when we are using the hot plate. What are the disadvantages? Basically, when we are using the acids in any experiments, definitely we need a high attention. So if you want to do the validation, definitely the person needs to be practiced and then needs to get a high attention for this experiment. And using the strong acids and combination of them, definitely they are corrosive. For that reason, these are basically the reagents that we are using is corrosive. And the sample size compared to dry etching is relatively low. I believe 10 to 20 samples you might be done, depending on how practiced you are. But if you want to do the dry etching to check the total etch content, then depending on the crucible that you are using, you may do like 40 to 60 samples at once. And another methodology besides the wet etching and dry etching, we also have the microwave etching. This is basically compared to the traditional methodologies for wet etching and dry etching, we use the microwave at the system. Basically, this is microwave assisting wet etching or dry etching that we can call. While we are using the microwave, overall, this is definitely reduced the time, required time for the assay, specifically for the microwave dry etching. It almost 97% time it reduced compared to the traditional dry etching. The dry etching mostly, as I mentioned, it takes around 12 to 18 hours, depending on the methodologies you use and also sample. But when you use microwave assisted dry etching, then you can complete this sample within few minutes. This is relatively, it reduces time, but overall, of course, it is relatively expensive equipment. You need a specific instrument to conduct this system. And also for when you are doing microwave wet etching, there are the open and closed vessel style instrument. And specifically closed one has some pressure at the environment, at the instrument, thus only using like one reagent like nitric acid that you can conduct for the microwave wet etching. And if your sample is really, if you need to analyze a sample like 10 grams, then there's also another option for the microwave wet etching, which is open vessel instrument. Then you can analyze a very large size sample using another type of the microwave wet etching system. And compared to the traditional wet etching, when you use the microwave assisted wet etching, overall it is less corrosive acid compared to the traditional one. And we can also analyze multiple samples within a shorter time, like 30 minutes instead of 2 hours for the wet etching, like few minutes compared to the traditional dry etching using the microwave system. This is the mostly advantages, even though at the beginning you need to spend a lot of money to get the system. So these are the examples. For instance, this is the closed vessel system. If you have a sample which is hard to digest, that you can use this system, only using the one solvent, one reagent like nitric acid, it is enough, and you can conduct the assay within 30 minutes, about 40 samples. But if you have the samples which make us, and also you need to analyze the like 10 grams of sample, there is another option for the microwave assisting, which is called an open vessel system on the left. And this is also this picture. This belongs to the microwave dry etching unit. As we see, this is kind of we have the heat through the microwave. Overall, for the etch analysis, as I mentioned, we have the wet and dry etching. So I have one question for you. For instance, what are the piece of paper? And next part of the lecture. So put your answer in there, and that will be for +2. Thank you, Karen. So, yeah. Yeah, I can give few minutes that you can address this two questions related to the main question. Do you need me to read the question if you are not able to see this screen very well? Okay, so basically, for instance, we are going to determine the total ash content of a product using the dry ashing methodology. And then your boss is going to ask you to use the wet ashing method instead of dry ashing method due to the, he or she said that it takes less time than dry ashing. So under this scenario, I have the two questions. So basically, the first one is that, do you agree or disagree with your boss concerning the time issue and why? This is your first question. And also, if you want to say, share, you can share with me. Yeah.
It might depend on the number of samples that you're scratching. If it's a lot, then it might not necessarily take less time.
We may not say because we are looking for the total ash content, which ash analysis we were doing to get total ash content. We have the dry ashing, wet ashing. So the dry ashing supposed to be total ash content, wet ashing to check the specific mineral profile of the sample, right? So do you think that should we agree with the boss due to the time?
I mean, it takes longer to do the dry ashing, but it's not saying what you want.
Yeah. Because we are just looking for the total ash. If you want to get the total ash for the food items what you are analyzing, you really need to do the only dry ashing. But if you are looking for, let's say, general mineral profile or the specific minerals, let's say iron you are looking for or calcium, whatever, then you need to do the wet ashing. This is basically, you can, due to the time, you cannot change the methodology. Basically, I almost addressed the second question, but still, do you want to say something for the second question? If we don't consider the time, what do you think? Should we continue for dry ashing or which scenario we can use the wet ashing? Yeah. Are we all done? Okay. Do you have any question about this? And basically from this table, we can see what are the general percentage ash for the different food items. For instance, basically, when you are analyzing any sample, you're supposed to check the literature or from the book, you can see what are the general ash content for the different food supplies. Then when you analyze your sample, you should expect similar ranges. This is one of the examples. For instance, if you are analyzing wheat flour for the dry ashing, you may supposed to get 1.6% wet, 1.6% ash in terms of the wet basis, which is acids. Overall, basically, when we are determining this is I think the lab you already started today. You were doing some experiment I saw. So you are going to do the ash content using the dry ashing method. And then I think you already started fat analysis today. I saw some of you at the lab. So we will be doing Soxalet and Mojangir methodology. For the measuring the protein content using for the different food items, we are going to use the nitrogen combustion method and Randall. And basically you are going to check the couple of other things based on this slide.
I have a question.
Yeah.
So dry ashing is for total ash content and what would be for mineral?
If you are looking specific to mineral profile, then you need to do the wet ashing because specifically due to for the dry ashing, we were using the oven like between 550 to 600 Celsius. So you may lose some samples due to the volatilization. For that reason, for the wet ashing, you need to follow the specific methodology based on the official methods.
So what ashing is usually done for specific minerals that could be volatilized with dry ashing. So, for example, iron and zinc, they can be volatilized and lost during dry ashing. But dry ashing is not only used for something. You can do like you did for atomic absorption. We did dry ashing with germanium, calcium, and iron sample. So you can do dry ashing for mineral analysis, but wet ashing you cannot get away from an ash. Your sample is oxidized and all of your minerals are solubilized in acid. So there is no weight of ash that you can get, so you cannot get percent weight of ash. So that's why dry ash is needed when you really need to calculate percent weight of ash. But for mineral analysis, you can do either. Unless the mineral is volatile, you can use wet ashing to prevent volatilization of the element during dry ash. Just because.
And also when you are doing the wet ashing, you may also supposed to do the dry ashing as well, because you may need to get total ash content. But if you just need to looking for the total ash content, of course, you are just going to use the dry ashing. You don't need to do the wet ashing, depending on what you are looking for. Okay.
Okay.
Thank you.
Why don't you clap for me when I finish? Jerry got the clap. Sarab got a clap. Did Samira get a clap too? Yeah. I'm jealous now. Okay. All right. We're going to move on to fat analysis. All right. Let's start with a couple of questions first. All right. So which of the following is true? The term lipid can be used for both oil and fat. Oil has higher melting point than fat. Fat has less saturated fatty acid as compared to oil. Elizabeth? A is true. A and only A. It's the other way around. Fat has a higher melting point than oil. So fat is the solid lipid, oil is the liquid lipid. Fat has more saturated fatty acids compared to oil. Okay. So the lipid portion of food can include vitamin A and B, consist of fractions with varying polarity, cannot be completely extracted using ethyl ether or diethyl ether. True? All of them. Vitamins A, D, E, and K actually are all fat-soluble vitamins, and they will be extracted with the fat component, so they belong to the lipid portion of the food. we have varying polarity. Triglycerides are very nonpolar, very hydrophobic, whereas phospholipids are polar lipids. Cannot be completely extracted using diethyl ether. Diethyl ether is a good solvent of lipids, but might not be able to extract all components of lipids. Usually when we do extractions of fat, we try to have combinations of solvents. Sometimes we mix diethyl ether with petroleum ether. So petroleum ether, for example, is really good for hydrophobic or very nonpolar portion of the lipid. So what is the definition of lipids? How would you define lipid? Maybe? What's that?
The smallest component of fat or the derivative of fat.
Derivative of fat is lipid? Okay, what other definition you can think of for lipid? What are lipids? When you hear the term lipid, what does it mean?
The storing of energy in the body is typically composed of carbohydrates and warm water.
There's a lot of compounds made up of carbon, hydrogen, and oxygen.
Yeah, but it's like if you use a somewhat of a biology.
Let's not think of biology right now. Good thing, but not the. You have to say something else? No? Go ahead. Yes, that's it. Lipids don't have a real definition other than those components of food that are not soluble in water, but soluble in organic solvents. That's it. Okay, so lipid can be simple lipids like esters of fatty acids. So your triacylglycerols, di and monoglycerides, other esters of fatty acids like vitamin A is an ester where instead of glycerol you have retinol. So these are your simple lipids. But there are lipids that have other components like phospholipids. So you have here 2 fatty acids instead of 3, but then you have a phosphate. So that's phospholipid, lipoprotein, glycoprotein, cerebrosides. So we have other components like just then your regular triglycerides. So you have potentially a protein component, a carbohydrate component, a combination of phosphate, nitrogen, and carbohydrate that could be in cerebrosides. So these are other forms of lipids. Derived lipids, that means like free fatty acids is derived due to hydrolysis of triglycerides. You have, when triglycerides are hydrolyzed, you have free fatty acid, you have free alcohol group, hydrocarbons, fat-soluble vitamins. These are all under the category of derived lipids. So this is your review of food chemistry right there, the lipid section in food chem. But what we care for in analysis is, why do we want to analyze fat content? Why is it important to analyze food fat content? Dora? Nutrition label. So, Grace?
It can affect rancidity and how much.
Stability of food, high fat content.
Just the overall shelf life.
Overall shelf life, yes, so stability, shelf life. What else?
It's important for how we go as far as like mouthfeel.
Yes, sensory attributes. You were gonna say that. Okay. Still gets a participation. Yes, Sandy. Health. Yes, exactly. Do we have, well, the total fat content calories? Yes, that's what relates to health. But also, when we talk about fat characterizations, that chapter later on, we look at saturated versus monounsaturated or polyunsaturated, omega-6, omega-3. Then it becomes a level of cholesterol, trans fat, then it becomes more related to health aspects. So here we're only talking about crude fat content. Then later on, we'll talk about different components of fat in the fat characterization. One last thing you guys did not mention is when we have standard of identity. So some products have standard of identity. You need to have certain amount of fat to call it whole milk versus skim milk versus 2% milk, for example, or different cheeses. Oftentimes, when you look at standard of identity, you have a specific fat content for standard of identity. So nutrition label, regulatory requirement, stability. One other thing we didn't mention is manufacturing specification. That doesn't, not every product or ingredient has a standard of identity, but you have specification. When you sell an ingredient, you have a specification of how much fat, protein, etc. this ingredient or this food product has. So manufacturing specification. There are a lot of analytical methods that are used to determine fat content. So we have a lot of different methods that we will talk about. And those, part of these methods are solvent extraction methods. So basically they're based on using organic solvents. And we have methods that are continuous. We're going to talk about an old method that I used when I was a graduate student called the goldfish method. I don't know why it's called goldfish. I don't know what the relationship is between it and the goldfish. There is no relationship. And then the semi-continuous, which you will be doing in the lab, which is Soxlet. And then you have the discontinuous, such as the Montagnier. And then there's this supercritical fluid extraction and then accelerated solvent extraction. And these both under elevated pressure and temperature category. And finally, you have the GC method, which is the same which you did. And this is the method that is used actually to determine fat content for nutrition label. Although Soxlet and Montagnier are official methods of analysis, they are not the one that the FDA approves for nutrition labeling. You have to do fatty acid analysis and count and add up all the fatty acids from C4 to C24, add the mass of them all, calculated as triglycerides, taking into account the glycerol mass, and then you get total fat content to put on the nutrition label. So keep that in mind. Although Soxlet and our Montagnier are official methods of analysis, they are not used for nutrition labeling as regulated by FDA. It is the same method that you've used in the lab, except that what you used in the lab, you didn't quantitate using external standards, but you would have to quantitate with external standards to determine the total fatty acid content and convert that to triglyceride. There are methods that are non-solvent based, and these are called non-solvent Lect extraction methods. We're going to talk about them. One is Babcock and the other is Gerber. Babcock has been developed at the University of Wisconsin. There's Babcock Hall there at the University of Wisconsin. Gerber is French. But both methods are mostly used for dairy fat termination. Instrument methods, IR. I'm going to cover still yet the IR chapter. I'm probably going to do that next Monday. So you can determine total fat content, moisture content, protein content with NIR or mid-IR, but it has to be calibrated with official methods of analysis. We're going to talk about that later. Foslet method based on density, specific density, and also NIR. Another way of determining. Okay, So we're going to start with solvent extraction methods. There's sometimes you have to do certain sample preparatory preparation to get to solvent extraction. And the most common one, you want to have a homogeneous sample. No matter what, you want to start with a homogeneous sample. You will break down the particle size to small particle size. So, homogenize the sample, grind the sample to increase surface area, and then you want to select the solvent to use. All of this depends on type of food sample, the nature of lipids. Do I have hydrophilic? Do I have polar lipids? Do I have mostly non-polar lipids? That determines what solvents I'm going to use. And then what extraction method is available for me. And based on the components within the food, I might decide that one method is better than another. So this here is a question that you had earlier, maybe in the first or second lecture. If you remember, to extract and analyze fat content in a food, the sample preparation may include, actually, no, that was chapter 5 when you saw this question. Okay, do we need to pre-dry? Do we need to acid hydrolyze? Do we need to reduce particle size? Go ahead, Anya. All of the above. Sometimes it's all of the above. Pre-drying is sometimes necessary for different types of food based on the method that we use. Some of you did that today, and we said for cheese samples, using sock-slit analysis, we need to pre-dry the sample. But if we're doing mojo on the same sample, we don't need to pre-dry it. So the only difference is in sock-slit, it's kind of static, there's no shaking. So if the sample has high moisture content, and then the solvent is trying to extract the fat, it's going to go through, and then there will be water there that might interfere with the solvent reaching the fat. And there's no shaking step to enforce the solvent to solubilize the fat. In mojo, there is a shaking step that allows the solvent to extract the fat regardless of the presence of moisture. So pre-drying is needed in one type of method and is not needed in another. And for sock-slit, if the sample has less than 10% moisture content, you don't need to pre-dry it. It's mostly for samples that are higher than 10%. Acid hydrolysis helps, especially for samples that have high carbohydrate or high protein content. So when you have high carbohydrate content, your fat is really associated with the starch, carbohydrate, fibers. It's really hard to get through and extract the fat component. So for those of you that did lab today, baby cereal, for example, high carbohydrate, we had to digest the sample with acid first to break down carbohydrate, to break down proteins, so that we can extract the fat component. For samples that are high in protein, but not necessarily carbohydrate, like cheese, instead of acid digestion, we do alkaline solubilization. And we did that in the lab today, where we used ammonium hydroxide to solubilize the protein and release the fat from the protein gel, which is the cheese curd. Okay, particle size reduction always, right? You always want to homogenize and grind your sample to small particle size so that you can increase the surface area to enhance extraction. So this is showing you percent fat obtained without acid hydrolysis and with acid hydrolysis. You see that with acid hydrolysis, we have higher fat content across the board. That means we were able to extract better the fat after we hydrolyze. Solvent selection. So we often, ideally, we want solvent that does not solubilize proteins and carbohydrates. We need a solvent that only solubilizes the lipid component of our food. Have low boiling point so that it can evaporate readily. So when we extract the fat, sometimes we extract the fat and collect the solvent and the fat, and then we need to dry the solvent to weigh out the fat. And so you want something that is easily removed or evaporate. Non-flammable, you don't want to cause an explosion. Non-toxic, non-hygroscopic. What does that mean? Hygroscopic means liking water. So diethyl ether, for example, is very hygroscopic. So it kind of gets saturated with water. And if it's saturated with water, it will become a less powerful solvent. So inexpensive. So great, wishful thinking, that's our wish list. Is there a solvent with all of these characteristics? One solvent, all of these characteristics? No, we wish there isn't. So sometimes, a lot of times, we just select the best solvent that we have based on what we know about the fat, based on our budget, and based on our experience. And sometimes we combine solvents. So it really depends on the method, depends on what's available, depends on the sample itself. But the most common solvents that we use for fat analysis, for fat content, using Mojo or Mojonier or Soxhlet are these two, diethyl ether and petroleum ether. So if we want to compare and contrast, which is a question in your lab report, to compare and contrast these two solvents. So diethyl ether is generally a better solvent for fat. What does it mean? It doesn't mean that it extracts all lipid components. It just means that it has affinity for varying types of fat or lipid components, non-polar and some polar. So it can extract triglycerides, it can also extract phospholipids. Not perfect for all components, but generally a better solvent for different polarities. Whereas petroleum ether is more specific for hydrophobic lipids. So if we know that our lipid components are mostly triacylglycerols, then it would be good to use petroleum because it's good for hydrophobic lipid and triacylglycerols are hydrophobic lipids. All right, so it is cheaper petroleum ether compared to diethyl ether. It is less hygroscopic, that means it does not get saturated with water as much as diethyl ether can. It's less flammable. If we look at the boiling point and a very similar boiling point with petroleum ether with a higher petroleum boiling point, but still it makes it less flammable. Whereas diethyl ether has more fire hazard. So what's the solution? Solution is sometimes mix both together, which we do for the Mojo or Mojonier. You'll see if you haven't done the lab yet, you'll see that in Mojo, we have a combination of diethyl ether and petroleum ether. All right, goldfish. This is the apparatus that I'm familiar with, and I have a story associated with it. But before I tell the story, I'll tell you how it works. So there's a picture of it, but I'm going to show you what's inside of here. But basically you have a hot plate. So these are heated plates. And then here is a condenser. So you have water flow into the condenser. And you have a hot plate where the solvent evaporates due to the hot plate, goes up into the condenser and condenses inside where we have a holder for your sample. Okay, so I will just try to draw this component so that you can see it. So first of all, you have a beaker. usually you pre-weigh. You can pre-weigh the speaker. And you put in here a certain amount of solvent, maybe 50 milliliter of diethyl ether or 25 and 25 diethyl and petroleum ether. And then this is your hot plate here. And there inside you have another glass container that there's a hole here, it's open. And then inside you have your thimble. So this is disposable tube that is porous, and that's where you weigh your sample in that thimble. And you place it inside of this glass compartment. So, and then here's your condenser. And you basically, you screw it on like that. And then what happens is when this is heated, so your solvent evaporates, goes up into the condenser and condenses into your sample, and then solubilizes fat and goes down into the container of your solvent. So it's a continuous extraction cycle. So goes up, down, take fat with it, and goes down, up and goes down. So here, basically, there is no soaking step. So in Soxlet, we're going to learn about it. There is a soaking step where the solvent soaks the sample and solubilizes the fat. Here, there is no soaking step. It continues, goes up and down. There is a risk of what we call channeling. That means your solvent goes through and down without collecting any fat. So it channels through. So this makes this process less efficient, might take longer time, might cause underestimation. And also is hazardous. And that's the story I have to tell you. I live to tell the tale. So I was using Saxon, actually I was teaching in a different university. And I was teaching a bunch of students. This was under the hood, and I was screwing this up, and I thought I did a good job screwing this up, and I placed it on the hot plate, turned the thing on, and then I was demonstrating to the student, but there was a leak that I wasn't aware of. So I was turning, and then the leak hit the hot plate, and boom, fire in my face. Burned my eyelashes, my front of my hair, and some of my face, but I'm still okay. I don't have deformation. So I never wanted to work with this anymore. And then I thought when I came here, there's no goldfish. I was so happy there was Soxlet instead. But there was another story to tell, and I'll tell you in a minute what happened. Okay. Soxlet, yes?
I just have a clarification question on the picture. So where does the sample start, and then after how this goes through, which part is it?
Okay, so the sample stays in your thimble. The sample of food that has fat is in your thimble. But here there's an opening. So this is a glass container. So you put the thimble in, and it's not closed, it's open. So your sample is contained in the thimble. It doesn't come out, but it's porous. The solvent can go through. So the solvent goes up, evaporates, condenses into the thimble, solubilizing the fat, and goes down back to the flask. So the flask here in the picture is yellow because it's just demonstrating that your fat ends up in this flask. You take the flask at the end of 6, 7, 8 hours of extraction, you take that flask, you evaporate the solvent, and then you weigh the flask that has the fat. Okay, Soxlet, some of you have seen it. It's semi-continuous solvent extraction. So here what happens, same principle, you have a hot plate, and you have, I don't know why this is not a great picture. We should update that picture. So you have a hot plate, you have a flask where you put your solvent. And usually you put about 300 to 400 milliliter solvent, 50 milliliter solvent, and you put that flask on the hot plate. Now, on top, you have a compartment where you put your thimble in it. Same thimble you used for the goldfish apparatus, similar one. It is porous, you have your sample in it, and then, but the compartment here is closed, so there is no opening directly to the solvent. So you put it in here. What happens, also you have a condenser here where water, cold water goes through. So what happens here, there is an arm, a thicker arm tube here. So your solvent evaporates, goes into this arm and up to the condenser. Condenses down into your thimble, and the solvent starts building up in this compartment and also in a small siphon arm or siphon tube. So the solvent starts filling up, so the sample is soaked with the solvent. So there is a soaking step. So this allows for better solubilization of your fat. So it's not, solvent is not just channeling through and going through, there is a soaking step. And then once the solvent reaches a certain height, there will be a pressure release from the siphon that is also being, the arm that is still also being filled with the solvent. It makes sense when you actually see it in the lab. And then it just, the pressure is released at a particular height, and then the solvent is released back into the flask. And the cycle continues 3 to 6 hours, depending on the fat content of your sample. And at the end, you have your fat here in the flask. You can also pre-weigh the flask and evaporate the solvent using a rotograph, but it takes a long time to evaporate 350 milliliters of solvent, right? It's a lot of time. But we don't do that. What we do for success is pre-weigh our thimble with the sample and then weigh it after we extract the fat. The weight difference is the fat extracted. Okay, because this would be a refatted sample at the end. Okay, so this looks to me, when I started to teach here, this looked to me a very contained system. So it was not until the very first lab we offered the analysis and we offered this experiment. It was set outside of the hood. That was a big mistake. So it was outside of the hood, and the TA at that time cranked up the heat and left it. The solvent in minutes evaporated, and there is an opening up here. So the solvent, instead of condensing down, it was coming out of here, the top, onto the hot plate. Nice. And I was standing there, PTSD, because of the goldfish apparatus. Told the student, don't panic. So nobody was panicking. It was me panicking. They don't know what happened. So they don't panic. Everybody leaves the lab, and I turned down the heat. Gladly, there was no explosion, but that was the last time we had it outside of the hood. It's now located in the hood. I stand by it, controlling the heat until there is no overflow, and it works perfectly now. So things learned. Okay. Both goldfish and success methods are gravimetric, meaning we take weight and measure weight after we defat. Either we measure the flask that had the solvent and fat in it, directly measuring it, or we measure the weight of the extracted sample. All right, on that same sheet of paper, let's do some math. And this math will be used for your lab report. If lab report, yeah, you'll do the same calculation. If percent fat on dry bases equal 15%, what would be the percent on wet bases if moisture content is 20%. You're actually going to do similar calculation because for cheese samples and salted analysis, we pre-dry. So the percent fat that you calculate is on dry basis. You need to convert that to wet basis as long as you know your moisture content. All right, so do the math. And that would be the last thing you do today. Just 30 seconds, do the math and keep that +2 sheet with you for next time. You don't want to do the math, Tyler? Huh? Okay, if you don't want to do the math now, we can do the math when you come back on Wednesday. Take the sheet with you and off you go. What? You did the math?
Where?
You did the math?
Do you have the?
I do have the answer. Huh?
Is it 12?
Yes. Okay, it's 12. All right, so basically what you do is you take the weight of your sample, of your percent of fat, you multiply that by 100 minus the percent moisture, and you divide that by 100%. This should give you, because now this is the dry matter. Okay, so this is 15 grams of fat in dry matter. And then if you wanted to get it on wet basis, which is 100 grams, that includes the 20 grams of moisture. That gives you the 12%. I can go over the calculation next time. I'll let you go, but here's the. No. Keep the, we're gonna do more calculations next time.
No, but if we do 2 calculations.